Hi, my name is Kate Chapman, and this is my Lab 4. So the purpose of this lab is to use an online simulator of circuits so that we can better understand and visualize the effects of resistors and capacitors. Key concepts that we use are energy conservation in regards to the loop rule, so the potential difference of a loop must sum to zero, and current conservation with the node rule that the current entering a node must be equal to the current leaving it. So both of these deal with the fact that energy and currents cannot be created or destroyed, merely transferred within the circuit. So part one, we set up a pretty simple circuit and we're asked to predict the value of I, which you can do because we know the voltage and the resistance. So when you do the equation, you get that the I should be roughly 0.2 amps. And then as you can see, that's exactly what it is. Next, we did an open circuit with a potential difference of 3 volts. The ammeter reads 0 because there's no current reading through since this is not a closed circuit. So yeah. So part one continued. This is the breakdown on top. It's the breakdown of the circuits and the wires and the voltage charge, different potential differences across each wires. And then when you put that into graph form in the bottom, you can see that it goes all the way up to 3 volts when you go to across the line BC. Or not, well, like across AB, it gets all the way up to 3 volts. But by the time it's made it all the way around the circuit, it is back to 0. And so from this, you can use a similar equation to the one we used before to find that the R47 resistor is about 47.9 ohms, and the R100 resistor is about 102.0 ohms, while the wire and the ammeter are both 0 ohms. So as you can see, this is pretty accurate because the 47.9 is for the 47 resistor and the 102 is for the 100 resistor. So we know that the ammeter reading will not change with the addition of a voltmeter because voltmeters have infinite resistance, which means that they don't affect the current. So we were able to go around and read all of these different charges with the voltmeter, knowing that it wasn't affecting anything. So continuing on, we then did a parallel circuit. We attached a voltmeter to the resistor, which again did nothing because it has an infinite resistance. But when the ammeter was added, the current changed to 0.6 amps. This is because the circuit is now in parallel, so the node rule has to apply, and the current is now split between the two junctions. This is also because there's now a path of less resistance for the current to pass through, whereas with the voltmeter, that path had infinite resistance, so the current wouldn't pass through it. So on to part two. This is dealing with a capacitor now. So when the first circuit is connected, the light bulb is really bright and the capacitor begins charging. As the capacitor reaches fuller and fuller charge, the light bulb dims until eventually there's no more light. When the battery is removed and the capacitor begins to discharge, the light bulb relights until the capacitor is completely discharged, where it once again resumes the off position. The 10 ohm light bulb took roughly 20 seconds to charge and to discharge, while the 20 ohm light bulb took closer to 40 seconds. So this is my data from the simple circuit up here for how long it took to discharge or to fully charge and discharge. So we were able to solve for RC. This is over the course of 20 seconds. So we were able to solve for RC, which I got to be about 6.8, which is definitely too high. because ideally resistance, RC should equal resistance times capacitance, which is 30 times 0.2, which should sum to 6, but it's relatively close. So I think there might have been an issue with some of my data somewhere. So for the most part, my data aligns with what should have happened and makes sense. While the RC was slightly skewed higher, it was still close enough that logically it made sense. So then some questions that we need to answer are, what if you're doing this experiment in real life? How would the ammeter change? So the ammeter would have had its own internal resistance, so that would have lowered the current being like the current that we were able to see and visualize being measured, which would have changed the results a little bit and made it less accurate. And then the battery and the capacitor, it should have taken much longer for the capacitor to charge. It wouldn't happen as instantaneously and quickly as it did in our simulation, because things aren't perfect and there is resistance in the wires sometimes, or just flaws in the circuit in general. And so sometimes the capacitor never even reaches its full charge. So that's all I've got for lab 4. Thanks.